Hi there. As we're heading into Lesson 7, Tangents and the Derivative at a Point, I wanted to have a few basic reminders. As we initially discussed last chapter, you could estimate the slope of the tangent line by looking at slopes of various secant lines and taking the limit as h approaches 0 in the formula for slope of a secant line. And that would give us a very good approximation for the slope of the tangent line. And then we said, well, we're going to get a little more formal here, and now we're going to call the slope of the tangent line at a point P this, okay? So this limit as h approaches 0 of f of x naught plus h minus f of x naught all over h, okay? That will be sort of our formal definition of the derivative, which is also the slope of the tangent line, which a large part of our discussion today is going to be the idea that the derivative wears many hats. The derivative is the slope of the tangent line, but it's also instantaneous rate of change at a point, and later down the road we'll also call it velocity. So we'll call it many things, but you're still finding the derivative. Okay? Let's see what's next. Notice in this next drawing, a little reminder here that note the difference between the words average rate of change and instantaneous rate of change. The average rate of change is over a given interval. Over an interval is the slope of the secant line, whereas the instantaneous rate of change at a point is the slope of the tangent line. Let's just visually investigate some tangent lines, some instantaneous rates of change on this graph here to the left, and notice how they change depending on where you're standing. So here the slope of the tangent line is very steep and negative. Here is still negative, but it's becoming less severe. And here is still negative, but it's becoming more and more flat. So it looks like the slope of the tangent line itself looks like it's flattening out, and possibly even approaching 0 as we level out there. Okay? So the idea is that depending where you're standing, the slope of the tangent line could be very, very different. And I'll just kind of reiterate what the author says here. The tangent slopes, steep near the origin, become more gradual as the point of tangency moves away. That's what we were noticing. Okay, and next, and I kind of said this, I got a little bit ahead of the game, but this is where we're heading. More formally, we say that the slope of the curve, y equals f of x at a certain point, is the number m, so notice that's a little m there, we're going to denote that little m. M is the limit as h approaches 0 of f of x plus h minus f of x over h, provided the limit exists. The tangent line to the curve at the point P is the line through that point P with that slope. So in our near future, we're going to have to find the equation of the tangent line using this sort of definition of the derivative here, knowing now that if we use the definition of the derivative, we are indeed finding the slope of the tangent line at a point. Okay? Definition of the derivative. The derivative of a function at x naught, denoted f prime of x, so more notation here, so f prime of x naught, notice, and that's why I drew the yellow lines here, notice they're the same exact thing. So whether we're looking for the derivative at a point, whether we're looking for the slope of a curve at a point, an instantaneous rate of change at a point, they're all calling for the same thing, the derivative. The limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so that's just notation. And I think, oh yeah, and this is just reiterating all the key points. The following are all interpretations for the limit of the difference quotient. The slope of the graph at a point, the slope of the tangent to the curve, the rate of change of f of x with respect to a given point, that's instantaneous rate of change, and the derivative f prime of x naught at a point. So you'll notice, you'll see all those interpretations, and they're interchangeable, and you'll see them in the text. think that takes us to the problems. That's the basics. Now we're ready to try some problems from the book together. Let's dive into number 5 here. I'll hit pause. Okay, so just in case the writing is a little small for you, I'm going to rewrite it. Y equals -1 minus 4x squared. They want us to find the equation of the tangent line to this function at a given point at 5, -101. So hopefully now you're thinking that we're going to get the derivative. Now, in our very near future, we're going to have all these shortcuts for finding the derivative, but now we want to find y prime using the definition of the derivative. So it's so tempting for me to use the shortcuts, but we want to use the definition of the derivative. So that's going to be the limit as h approaches 0 of f of x plus h. So notice that I'm just taking -1 minus 4x plus h, whole thing squared, so there's f of x plus h, minus the original function all over h. Okay, so now we crunch that out. It's going to be a lot of just algebraic cleanup is all that is. You're going to want to FOIL this out, clean this up, and evaluate. So I'll hit pause as we do that. So we arrive here, and you can see that, if you clean that up appropriately, there's going to be a lot of cancellation. So you're going to have -1, minus 4x squared minus 8xh minus 4h squared, plus 1 plus 4x squared. And notice here, you might be wondering, I distributed this negative, and that's how I arrived here. Okay. Now you'll notice, okay, all of that over h. You'll notice that this cancels with this, and this cancels with this. And if you divide out by this term and this term, divide out by h, right? So you're going to be left with -8x minus 4h. I'll hit pause. But if you take the limit as h approaches 0 of -8x minus 4h, if you do that, that term there is going to go to 0. You're going to be left with just -8x. So after all that sweat equity, your derivative is, which is the slope of the tangent line, is -8x. Now what we want to do is evaluate that. Remember that given point was 5, -101. So we want to evaluate that, at x equals 5. So at x equals 5, notice, -8 times 5 is -40. So now we know the slope of the tangent line is going to be -40. Okay, so now we know equation of the tangent line, y equals mx plus b. And actually, before I go and do that, I just want to make sure you highlight all the critical information. Y prime ended up being -8x, and if you evaluate that at x equals 5, you get the slope of the tangent line, basically I'm going to denote that little m, is -40. Okay, I'll hit pause so we have more room. Okay, so I just kind of cleaned up the screen and gave us some more room. So we have our original function. We know the derivative evaluated at 5 now is -40. We're looking for good old y equals mx plus b, the equation of the tangent line. So now we know y equals, -40x plus something. And you say, how am I going to find that something? I'll do this in another color. Pretty simple. You just, good old algebra, you plug 5 in for x and plug -101 in for y, and you crunch it out. So -101 equals -40 times 5 plus b. Solve for b, so -101 equals -200 plus b. Move 200 to the other side. So b equals whatever -101 plus 200 is, which is 99. So now let's try and type that in. So you can see here I typed that in, and negative 40x plus 99, and we did okay. And then it says generate similar exercise, but we're good with that. Now we want to try the next one on the checklist, which was number 13. Let's see if I can grab that one. This says find the slope of the graph of the function y equals 6x over x plus 2 at 4, 4, and then find an equation of the line tangent to the graph at the point. Now, this one, I know at this moment we're supposed to do definition of a derivative. We saw the previous example how to do that. What I'm going to take you through right now, though, is the quotient rule. For time's sake, we're going to be playing with the quotient rule, the rest of the chapter. So let's just, for time's sake, go ahead and use the quotient rule, so we can find the equation of the line tangent to this. Okay, so y prime, I call it low-d high minus high-d low, low-low. This is a bottom times the derivative of the top minus top times the derivative of the bottom over bottom squared. Okay, so bottom function. Oh, and if you, just in case you can't read the original function is 6x over x plus 2. Okay, so bottom function times the derivative of the top function, which is 6, minus top function times the derivative of the bottom function. What's the derivative of the bottom function? 1 all over bottom squared. Okay, so that's, finding the derivative using the quotient rule. It says find the slope, at the point 4, 4, so we would have to plug 4. Everywhere we see an x, we'd have to plug 4. So, we'd have 4 plus 2 times 6 minus 6 times 4, all over 4 plus 2, which is 6, squared. Keep crunching that out, and we'll have the derivative evaluated at 4. So 6 times 6 is 36, minus 24 all over 36. We keep crunching that out. 36 minus 24, is 12, and 12 over 36 is a third. So after all that sweat equity, we arrive at a third. And, a lot of people say, why did you use the quotient rule? Because I'm having some foresight here, knowing that we're going to know all these shortcut rules for the derivative by the end of the chapter. So just kind of saving some time on the podcast there. So 1/3 then is the slope of the tangent line. So remember all of that. What did that give me? That gave me the slope of the tangent line. Okay, so now we know y equals 1/3 x plus something. And how are we going to find that something? We're going to have to take that point that they gave us, 4, 4. The given point, 4, 4, is the x and a y to plug in. Well, if I do 4 equals 1/3 times 4 plus b, I could solve for b. So b ends up being whatever 4 minus 4/3 is. Which is 8/3. Okay, so now all that solving, we arrive at 8/3. Let's try to type that in for the, well, actually at phase 1, I just noticed in phase 1 they're just asking us for the slope, which is a third. I'm going to write that down. So slope is a third, and full-blown equation is a third x plus 8/3. So you see I typed in the slope as a third, and it said okay. And then equation of the tangent line, and we said that's going to be 1/3 x, and then plus 8/3. Good. All right. And And then I think I don't want this podcast to be too long, so I think I'm going to do one more on here and then make a separate podcast. Okay, so we'll do one more here together. We have y equals 2x squared plus 2x minus 8. They're asking us find the point at which that function has a horizontal tangent. Note to self, if the tangent line is horizontal, I'm going to do a little bit of translating here. What's its slope? 0, right? So, again, I'm going to kind of cheat and use our shortcut rules for getting the derivative. And I don't want to go through the definition of the derivative for every single problem. So y prime equals 4x plus 2. Okay. Now we have the derivative. We want to know the point at which, the function has a horizontal tangent. Now, by the way, I'm just saying, we could graph it. It's a quadratic, so you could, in theory, graph it and see where the absolute min or max is. In this case, a min. But, you could graph it and figure out where that point is. But we're trying to do calculus here, right? So we'll do it algebraically. So, then the question is, when does 4x plus 2 equal 0? Question. Because that's, when does the slope of the tangent line equal 0? Solve that out. You'll get 4x equals negative 2, or at x equals negative a half. Oops, pen's being fussy again. So at x equals negative a half, let's just type that in. Oops, didn't like that. Must have done something wrong. Let me patch that up. I realized what I did wrong. That's the x value. It was right, I just didn't type in. It says type in ordered pair. So up here it should be negative a half comma something. And so that should be negative a half comma. And then if you store negative a half into the original for x, you'll see the corresponding y coordinate of negative 8.5. And I guess it wants parentheses since it's an ordered pair. I'm assuming it wants parentheses. Yay! So it just wanted an ordered pair. And again, I did want to mention, if you're more of a visual type person, you could, just take a look at the graph of the thing and, where does it, there would be a horizontal tangent right there. So you could, in theory, find the min of this here parabola, and that would answer that same question, rather than setting the derivative, to 0. Okay, hope that helps. I'm going to do the rest of the problems on another podcast.